Good morning, everyone. I am Dr. Vivek Jain, working as an assistant professor in the Department of Electronics and Communication, Madanapalle Institute of Technology and Science, Madanapalle. So, first of all, I am thankful to management and my department head to provide me this opportunity to be here before you for delivering some lecture. So, I am very thankful to management. Here my presentation topic is semiconductor theory under the area of electronics, and the flow of presentation includes these are the important points: introduction, energy band diagram, material, intrinsic semiconductor, extrinsic semiconductor, mass action law is very important, and this one is very important, current flow. So we will discuss current are two types. One is drift current and one is diffusion current flow in semiconductor and references. So introduction slide includes these are very important points. The electronics. So electronics is basically electron per plus mechanics. So ultimately motion of electrons. So we can say it is the field of science and engineering which deals with the motion of electrons. This is the definition of electronics. Now come to the electronic devices. So electronic devices, maybe semiconductor devices, diode, transistor, amplifier. So to performing important functions like amplification, rectification, generation, and control, that is switching. So these are major important functions performing through the electronic device. Now come to the matter. So matter is what? Anything having we can say some space and some weight. Now matter consists of molecules, and molecules can be subdivided into atoms. And atom we talk in our semiconductor theory, that is silicon and germanium. Now come to the electric field. So this is very important term related to our electronics, that is electric field intensity and electric field. So we know very well field means area. So here we discuss electric field. So definitely we talk about charge, positive charge and negative charge. So if we talk atom, so atom consists of mainly core, and core contains proton and neutrons, and electrons are revolving in the orbits around the nucleus. So proton having positive charge and electron having negative charge. So when we talk charge, so definitely we talk force, and after force, definitely we talk electric field. So force may be attraction if charges are opposite sign, or force may be repulsion if charges are uniform sign, means both are positive or both are negative. So electric field is the area when some stationary charge feels some force due to other charge in that field. So this is electric field, and electric field intensity is given by force per unit charge. So this is very important term. Now come to the potential or voltage. So it is also very important term. So it is defined as the ratio of work done to the charge transferred. Now potential energy. So this is given by charge into voltage or force into distance. This is very important formula, and unit is given as joule or electron volt. And other one is the kinetic energy. So kinetic energy is given by half mv square, where m is the mass of the particle or electron and v is the velocity. So total energy of the electron can be given as a potential energy plus kinetic energy, and overall energy of the electron is negative. Now come to the energy band diagrams. So this is also very important term, energy band. You know the band is the, we can say, uh, uh, group of some energy lines. So that's why we called energy band. Energy lines in terms of electron volt. So energy band theory, this is very important, explain the interaction of electrons between the outermost cell or and innermost cell. We know in nucleus there are orbits around the nucleus. In orbits, electrons are revolving. So band diagram is the diagram plotting various key electron energy labels. These are very important energy labels as the function of some spatial dimension. Now this is the basic energy band diagram of the, we can say, material. Material are having maybe conductor, semiconductor and insulator. So you can see in the picture, the first one is, you can see, first picture is related to the insulator. So here you can see energy gap is much more, that is 6 electron volt between the conduction band and valence band. So conduction band having responsible to flow the current through the free or free electrons. In second, you can see this is the structure for semiconductor. So here the energy gap is 1 electron volt. So this is our desire for electronics, that is semiconductor. And third one is, you can see no energy gap. This is the picture for the conductor or metal. So here no energy gap between conduction band and valence band overlaps. So our, this one middle, you can see here energy gap is 1 electron volt. So electrons from valence band can be moved or jumped from valence band to the conduction band using some different methods to provide energy. So electrons may be jumped to the conduction band, and when electron comes into the conduction band, that is called free electron, and only free electron we can flow the current. Now come to the material. So already I have discussed material consists of maybe insulator, conductor and semiconductor. So if we talk insulator, so already no conduction, do not conduct at room temperature, and very wide forbidden energy gap 6 electron volt. So practically impossible for an electron in the valence band to jump the energy gap and to reach the conduction band. So it is impossible. And we can see some examples: diamond, glass, plastic, rubber, porcelain. So many examples in which no current flow. Next one is the conductor. So conductor can conduct at room temperature, bands overlap without applying additional energy like heat or light, contains large amount of free electrons. So here the examples of metals, that is aluminium, aurum, copper, iron. Now come to the our desired material, that is semiconductor. So dependent conduction we need, because we have to control the current in the material, or we can say we have to control the current in electronic devices like diode, transistor, and these devices consist of semiconductor material, that is silicon. So here conductivity can be changed or varied by thermal or optical energy excitations. But at 0 degree Kelvin, semiconductor also behaves as a insulator. But our purpose, we can say, that is room temperature. So semiconductor allow excitation of electron from lower energy level, that is valence band, to the higher energy level, that is conduction band. Examples are silicon and germanium. So silicon and germanium, these are elemental. And if we talk compounded, that is gallium arsenide. Now we come to the little bit about energy band gap, maybe direct band gap or indirect band gap. So here only difference taking potential energy and momentum. In direct band gap semiconductor, when electron jumps from valence band to the conduction band, so here only the change in its potential energy only. Examples are gallium arsenide, indium gallium arsenide, gallium nitride, cadmium sulfide. These are the, we can say, compounded. Now in indirect band gap semiconductor, when electron jumps from valence band to the conduction band, so will change potential energy and also momentum. So examples are silicon and germanium. So silicon is our desired material, semiconductor material. Now this is the picture, we can say, covalent bonding for the silicon atom. So here first we are discussing intrinsic semiconductor, that is silicon. So here you can see the picture silicon. Silicon atom having 4 balanced electron in the outermost cell, or we can say balanced cell. And this is the purest form without adding any impurity or dopant. So here you can see sharing the electrons one covalent bond consists of two electrons. So covalent bond having, already I have discussed, intrinsic semiconductor. Here ISC means intrinsic semiconductor having 4 electrons in the outermost shell, and each atom attempt to acquire 8 electrons in its valence cell. If we talk 3-dimension structure or crystal, so definitely 8 electrons are there. Now, already I told 1 electron from each 4 neighboring atoms sharing 1 electron. This sharing of electron in the semiconductor is known as bonding, or we can say covalent bonding. Now come to the charge carriers in the semiconductor. So charge carriers are very important term, because these are the cause to flow the current. So at 300 degree Kelvin, or we can say at room temperature, semiconductor atom, that is silicon, get sufficient thermal energy. So valence electron moves from influence of the valence electrons can move from valence band to the conduction band, and covalent bond can be broken. So a vacancy, we can say, that is hole, is created in place of that broken covalent bond, known as hole. So electron EHP means electron hole pair. So probability to occur electron hole pair generation. Now continue to charge carrier. So here we can say concentration of free electrons and holes are same in the intrinsic semiconductor. It is denoted as a intrinsic concentration and given by N equal to P equal to this one Ni. N is the number of free electrons, P is the number of holes, and this one is the same structure in previous slide we have seen, and this one is the energy band diagram of the semiconductor. So you can see this one is valence band, this one is conduction band, and between energy gap is, so conduction band electrons are the free electrons which are required to flow the current. Now this one is the important formula to find the intrinsic concentration, that is given as Ni square equal to, this is very important, A0 T power 3 e power minus Eg, Eg naught, that is energy gap at 0 degree Kelvin, divide by kT. So K is the Boltzmann constant in electron volt per degree Kelvin, and T is the temperature in Kelvin. So we can find the intrinsic concentration, and A0 is the material constant. So easily we can find intrinsic concentration for any temperature. Generally we use the room temperature, that is 300 degree Kelvin, and intrinsic concentration we can find. So already I told for T equals to 300 degree Kelvin, that is the room temperature. So putting the value here, you will get Ni, that is intrinsic concentration. That is very, very important. This is fixed for silicon, 1.5 into 10 to the power 10 carriers per centimeter cube. So this is very, very important. Now come to the effect of temperature on the conductivity of the intrinsic semiconductor. So already I told semiconductor at 0 degree Kelvin behaves as a perfect insulator. But at room temperature, some electron hole pair are generated, and as we increase the temperature, electron hole pair generation increases. So at high temperature, more charge carriers are available to flow the current or for conduction. So conductivity increases with increase in the temperature. So we can say semiconductors have negative temperature coefficient of resistance. Now come to the extrinsic semiconductor, which is required to manufacture our electronic devices. So simply, so here we can see carrier generation due to external energy like temperature and light, or using doping. We can create for using doping, we can create extrinsic semiconductor. So extrinsic semiconductor may be p type or n type. So conductivity can be increased using doping. This is our purpose. And predominance of either hole or electron depends on the impurity we are using. Now we can see this one is the n type. So n type, n for negative, and electron having negative charges. So we can see here the major or majority carriers are electrons. And we use pentavalent impurity. So 4 electrons are, we can see, say 4 electrons are making a covalent bond, and 1 electron is the free electrons. That's why here the conductivity due to electrons. So this is called n-type semiconductor. Come to the next one, that is uh, uh, next one is n-type semiconductor having, this one is the energy band diagram. So here we talk donor energy level. So you can see in the picture, this is just below to the conduction band, or we can say very near to the conduction band in case of n-type. And here n is greater than p, means number of electrons are greater than number of holes. Now come to the p-type semiconductor. So here what happening, p is the positive, p means positive. So here we talk hole. So the majority carriers are hole, and hole is created in the covalent bond due to lack of electron. So we assume there is some vacancy in the covalent bond, and it is treated as a hole. So here holes are the major or majority carriers. and p-type created using the doping that is trivalent impurity: boron, aluminium, gallium, indium. Now this one is again, here you can see, here we talk acceptor energy level, so it is just above the valence band, and here P is greater than N. And these are the some doping labels: moderate doping, lightly doping, highly doping. So moderate doping, one impurity atom in the 10 to the power 6 silicon atoms. If we talk lightly doped, so one atom, impurity atom in 10 to the power 11 silicon atoms. Or if we talk highly doping or heavily doping, so here one impurity atom in 10 to the power 3 means 1000 silicon atoms. So silicon atoms are reducing means highly doping. Now this one is the mass action law. This is very, very important. That is Np equal to Ni square. We have discussed Ni is the intrinsic concentration and N is the number of electrons, free electrons, and P is the number of holes. So the product of both always equal to the Ni square or square of the intrinsic concentration. This is very, very important formula. This one is the charge neutrality theorem. So here we can say number of holes and plus donor atoms is equal to the number of electrons plus acceptor atoms. Here Nd indicates D for donor, number of donor atoms, and Na, A is indicate, that is number of acceptor atoms. So always this one is left side total positive charge and right side total negative charge. So always charge neutrality theorem says charge cannot be produced or destroyed. So total positive charge equal to the total negative charge. Now this one is the current flow in the semiconductor. This is very, very important. Current due to maybe diffusion or drift. So these two mechanisms are very, very, very important in our semiconductor theory. So you can see drift and diffusion. So only two words are important: drift current due to electric field. And electric field is what? Potential gradient. So simply we can say drift current due to potential gradient, and diffusion current due to non-uniform concentration of the carrier. Carrier may be hole or electron. So non-uniform concentration, we can say concentration gradient. So drift current due to potential gradient and diffusion current due to concentration gradient. So this one is the drift current. So here you can see when electric field is established in the semiconductor crystal, then drift current can be. So electric field is the cause. Now holes are accelerated in the direction of the electric field, and electrons are opposite direction of the electric field. So free electrons are opposite. Now if holes are same direction, so we can write the drift velocity of the hole. Vp means velocity, drift velocity of holes. It is given by, this is very important, mu. Mu p means mobility of the holes multiplied by the electric field. So this is very, very important. formula to find the drift velocity of the carrier. Carrier may be hole or may be electron. So mu p is called hole mobility if we talk electron. So here p is replaced by small n, means we can see Vn is equal to the mu n multiplied by electric field. Now this one is very important, drift current density. So if we talk density, means per unit area. If we talk current density, means per unit area. Or if we talk charge density, means per unit volume. So here very simple formula, current density is given by current divided by area. Area is denoted by A. So after using some formula, these are very important formula. Current is denoted by charge per time. So using this one, so we can put here the value of current, and after simplifying, we will get this one, charge density. J is the current density, is equal to the rho V, where rho is what? This is charge density. So this is very important formula, and V is the velocity. So this is very important formula, J equals to rho V. For metal, so only we talk electrons only. So here this is the formula, J equals to sigma E. But if we talk semiconductor, so both are the carriers. So we take for both carriers electron, that is Jn, plus for hole, that is Jp. So the total current density given by this one, this is very important formula, n mu n plus p mu p in bracket and multiplied by QE, where mu n is the mobility of electron and mu p is the mobility of the hole. Q is the charge and E is the electric field. So this is very important equation for to find the drift current density in semiconductor. Now come to the diffusion. So diffusion current, already I told, due to concentration gradient. Concentration gradient may be due to holes or due to electrons. So diffusion current take place. So here we talk, suppose x is the distance, so we can write concentration gradient as like this one, dy dx of n, that is dn upon dx also. So here you can see highly doped or number of carriers are more, and here number of carriers are less. So it is like non-uniform concentration according to the distance x. Now these are the some important equations when we talk diffusion current density. Here capital Dn, that is diffusion constant, and n for electron, and here dp, diffusion constant for hole. So for electrons, simply current density is proportional to the, already I told, concentration gradient. So if we talk electron current density, so dn upon dx, or if we talk for holes, so dp upon dx. So simply is proportional, this one is proportional sign. So if we take equal sign, so simply we multiplied some constant, and that constant is given by dn and denoted as a diffusion constant. And for hole also, it is given by dp. So it is also diffusion constant for hole. So these two are the very important formulas for finding diffusion current. These are the references in which Sadra Smith that is microelectronic circuits, are very good book. Thank you very much for listening patience